always, we're going to have all the talks up front. Each speaker has 15 minutes, and then we'll have follow-on Q&A sessions at the end of the session. So first up, we have Oscar Key from University College London. Please, Oscar, the stage is yours. As a reminder, please use Slido for the questions if you're having any questions you want to ask.
Nice. Yeah, so maybe it's hard to follow a talk about the deep learning revolution in data assimilation with a talk about sort of more conventional data assimilation, but I'm going to give it a go. So yes, I'm going to talk about this new method for data assimilation that we've been playing around with, and its work with my collaborators, and Dan and Mark. Actually, I don't know if Mark is here, but Dan is definitely here, so you might have bumped into him. And so, yeah, I'm just going to talk about what the scalability challenges are in data assimilation, and then the method we've been working on, and then some very initial results. Let me just put a clock on. Oh, there's one there. Oh, perfect. Thank you. OK, yeah, so I should say that I guess I'm interested in scalable machine learning algorithms generally. I don't really know too much about data assimilation, but my interest in scalable algorithms is how I've come to this problem. And so here is an amateur's perspective on numerical weather prediction, which is where we have this simulator of the atmosphere. And what we're going to do is update our simulator using current observations of what's going on the Earth. And then we're going to roll out the simulator in order to predict future weather. And so this first bit is, of course, data assimilation, and that's what we're going to talk about today. And so here's a bit more detail on data assimilation. So here we've got the atmosphere, and we've conveniently simplified it to 2 dimensions. And then it's going to be divided into a load of cells. And in each cell, we're just going to represent the state of the atmosphere in that cell with some weather variables. So here I've plotted the surface temperature, which is from era 5, and then, but pressure and loads of other things are also going to be represented. Of course, in reality, the grid is much finer than this, but just for illustration. And then in data assimilation, we're going to combine that with some observations. And so here I have drawn some satellite observations. So here are some satellite tracks. And we're going to combine the current state with the observations in some sort of inference process, which is going to combine it with the physics of the model to come up with an estimated state. Is the data assimilation algorithm. Oh, maybe this bit in the middle is the data assimilation algorithm. And that's what we're going to talk about today. And commonly, people use 3 or 4D VAR for doing this at the moment. And those are sort of optimization-based methods. So we have an objective, which is a function of the state of the atmosphere. And then we're basically just going to optimize that objective. But then, of course, the problem with this is that the atmosphere is really huge. And the data involved is also really big. So we don't have enough memory on one computer to do this. And it would also take a very long time if we just used one computer. So instead what happens is we need to do some sort of distributed computing approach. And my understanding is that the way this is usually done is through a technique called domain decomposition. So here what we do is we geographically split up our model of the atmosphere among lots of different computers. So you can see we've split a little bit here, a little bit here, a little bit here, a little bit here. And then each one of these is going to locally solve the data assimilation problem for the bit of the atmosphere that this computer holds. And then at the end, we're going to stick all of these local estimates back together to get our global estimate of the atmosphere. But the problem with doing this, if you do it naively, is that now, if we solve it locally up here and solve the problem locally down here, then on the border region, the 2 local estimates might not be consistent. So we might get some sort of, stuff that doesn't physically make sense, like we might get sudden jumps in pressure or something like that. So we have to do some sort of synchronization between these regions to avoid that problem. And here's one solution, which I think is potentially commonly used. So what we do here are where we have extended the subdomains so they overlap. So now the bit in the blue region is both in this subdomain and also in this subdomain. And so then what we do is during the optimization process where we're trying to estimate the state in the subdomains is we very carefully do some work to ensure that the state in these areas is synchronized. So that means that it's physically consistent between this subdomain and this subdomain. And so that works, but the problem is that now we've introduced quite a lot of communication because we have to ensure that these regions are synchronized. And the problem with communication is that that's between different computers in the data center or whatever you're running this on, and communication between computers is much, much, much slower than computation within a single computer because of the distances involved, basically. So this basically causes a scalability problem, and you can see that the sort of finer your grid gets, potentially the bigger this scalability problem gets. And so is this a real problem? Well, we hope so, and indeed, in this report from the ECMWF, they talk about this a little bit. So they're talking about basically like increasing the amount of data processed by data assimilation. And so they have this quote: increasing the spatial parallelism, so I guess dividing into more subdomains, would not be sufficient due to increasing communication overheads. So I guess that's what we've been talking about. And then they say there is a clear need to develop more parallel data assimilation algorithms which better map to the available resources. So yeah, I guess algorithms that better suit the kind of compute we have in a data center. And so, you know, maybe these are deep learning based approaches, but maybe it's this, who can say? Okay, yeah, so then we've been trying to solve this problem with message passing. And the convenient thing about message passing is that it is a naturally scalable algorithm, so it doesn't suffer from this synchronization problem to the same extent. So then, what is message passing? Well, message passing is a big family of algorithms, but we're particularly interested in the ones that you can use for doing Bayesian inference. And so for people familiar with this, our algorithm is kind of a variant of Gaussian belief propagation. So the input to the algorithm is a probability distribution, a joint probability distribution over a load of variables, which can be expressed in this particular formulation, which I'll talk about in a minute. And so we put in this joint distribution, and then we get out the marginal distribution over each of the variables. And so what does this look like in our case? So the input, we basically are going to express the SPDE that's encoding our atmosphere simulator in this form, where so these F things are all of the weather variables, and then the Y's are the observations. And then at the end, we're going to get out the updated state of each weather variable, so the updated state at each grid point. And so what is this representation here? Well, you can see that this is kind of encoding a graph on the weather variables. So each one of these F's is a weather variable, and then this here is what's called a pairwise factor, and so that indicates that two weather variables are connected in the graph. So message passing is kind of doing some sort of computation on this graph representation of the weather variables. And you can also see that we're talking about getting a probability distribution out at each weather variable. And so initially when we started this, we were hoping this was going to be super cool because not only would we get a mean prediction of the updated state, but we would also get some sort of measure of the uncertainty of the updated just as a predictive mean. So then let's go into a bit more detail of our approach. So in this paper, we're only looking at 2D spatial inference, massively simplified data assimilation problem, of course, but the whole thing is designed to be extended to 3D spatial temporal inference. So stage one is we take our SPDE and we discretize it using finite differences, but you could use some more complicated discretization scheme. And then from this, we factorize it into this graph representation. And so this is a sort of simplified version of the graph. So you can see we've got all of the weather variables here, and then we've got these edges between them. And so these edges kind of encode the relationship between adjacent weather variables in the SPDE. And then we're going to perform message passing. And so what message passing is kind of a pain to explain. But I've tried to come up with some sort of intuition. So what you can see here, it's an iterative process. And so in each iteration, what we do is each node in the graph basically receives messages, so updates from its neighbors. And so each neighbor is saying, this is what I think my current estimate of my value is. So say we're doing surface temperature, it's an iterative process. It's like, I think, I have this temperature. And then this node is going to combine the best guess estimates from all its neighbors. And then using its knowledge of its relationship on the edge, which is encoded by the differential equation, it's going to come up with its best guess of what its estimate is. And then it's going to send that best guess to all of its neighbors. And then this process kind of iterates, and that's how we update the estimate. And so to try and give a better intuition, here I've got a 2D example of some message passing. So here you can imagine this is like a very coarse temperature field. And so at initialization, we've got observations at each one of these dots. And so at initialization, the cell at the observations has the value of the observation, but then all the other cells in the grid are just set to some prior value. And then we can start iterating message passing. And so you can see in the first iteration, we can see the data sort of slowly starting to spread out from the observations across the grid. So you can see it's now moved to sort of like the neighbors. And then if we do another step, it's moved a bit further, another step, moved a bit further, and so on, and so on, and so on, until we get kind of like a final estimate of the temperature in the field. Yeah, so I hope that sort of roughly made sense. It's my best effort. Okay, so then the question is why is message passing more scalable? So what's super convenient about it is that because, the really important thing is that each node is only communicating with its neighbors. And so what this means is that we don't really care like how the graph is split up. So we can easily split the graph up among different compute nodes, and we only have to exchange the messages on the border between the compute nodes. And this is a really small amount of data, so that makes it quite scalable. And we can also imagine that there's no requirement that these messages across the border are updated sort of in sync with the computation that's going on the individual nodes. So you can imagine a scheme where we basically do the computation on the individual nodes as quickly as possible, and then every now and then, as best effort across the network, update the messages going between the nodes. So we actually haven't tried this yet, but that's the theory. And so maybe what I'm going to do next is see if that plays out in reality. And then the other thing that's convenient is because of the discretization, we have this like really regular graph structure. So you can see, I mean, this is simplified, but the true graph is not that much more complicated than this. You can see we've got this extremely consistent graph structure. And so this makes it extremely amenable to GPU computation. And obviously for this kind of thing, GPUs are much faster than running on the CPU. And so nice JAX implementation of this thing, and it works pretty well. All right. And so, yeah, so just finally, here are some initial kind of like slightly toy results to see if it kind of works at all. Yeah, here is a, so I guess the headline is maybe it seems like a feasible approach, although we've only looked in this really simplified setting. So here you can see a nice picture of it working to infer this surface temperature field. These we're using observations on these satellite tracks, and then we're able to infer the field, although we use ERA5 as a prime mean. So that's nice. But then I've got this huge, horrible table here. And so the second part of the headline is, so far, it often seems to be slower than our GPU-accelerated 3D VAR implementations. So what is this thing? Well, I just wrote a sort of bare-bones 3D VAR implementation in JAX, just a very simple one, and that turns out to actually be extremely fast. And so in this table, you can see we're looking at different grid sizes and different observation densities. And the RMSE, so this is again in Kelvin because it's temperature, basically it's comparable in terms of the final error, but in terms of computation time, we do all right, for example, here, here and here and here, where we have high density observations. But when the observation density, because you can imagine message passing is kind of like spreading the information out across the graph. And so if the observation density is lower, it takes longer for the information to spread out. And this last row, we do really badly, but I think there's some particular reasons for that I won't go into now. So then future work. At the moment, we only do 2D and no time, so we want to do a sort of fuller problem. And also maybe it would be interesting to try and hook into these machine learning forward models. I think there's some things we can do to improve the performance. And also, we make all these claims about being better for distribution, but we haven't actually done that yet. So, you know, that's something we need to do. Yeah, if anyone's interested, that's all I got.
Thanks, Oscar. And I think we have a tech changeover before our next speaker, Dr. McNeall from McNeall. And at the same time, I want to give credit to Katie and Lele, who has been running around for the entire 3 days, and they are the first one arriving on site, and then the last one to leave this place whenever we're in a session. And that it's really stressful. So please give a hands up for Katie and Lele from the Turing team. All right, I started enough. Now it's like now it's time.
Hi, I'm Doug McNeall. I'm from the Met Office, and I also work at the Global Systems Institute at the University of Exeter. And I'm here on behalf of my team, the Earth System and Mitigation Science team in the Hadley Centre. So today we're looking at, will a climate simulation run? So here's the problem. We've got a brilliant land surface model. It's called Jules. It's a community model, so it's built by us and by our partners. And it is part of a broader system, the UK Earth System model. And really, we'd like calibrated historical and future projections of the land surface and particularly the carbon cycle, because that impacts our remaining carbon budget, for example. So as a team, we're pretty focused on building these land surface models and informing, say, government policy about remaining carbon budgets and the future of the carbon cycle. So Jules runs fairly quickly, but it's still fairly costly. And really, it's covering the land surface in terms of forests, agriculture, cities, ice, this kind of thing, carbon in the soils and in the land surface, the exchange of heat, momentum, and water and carbon between the land surface and the atmosphere. So as I say, it's a deterministic model. So if you run it at a particular set of inputs, it gives you the same answer each time. Those inputs are uncertain, and these inputs, we've got a bunch of uncertain inputs in the model, which are basically maybe exponents within equations or constants that are worked. So these are uncertain, and as I say, it's deterministic, and it's relatively computationally expensive. We'd like to minimize that cost if we possibly can. So a similar setup to if you saw Tamsin's talk yesterday. We're in that kind of world. So here's a really nice way of looking at that graphically. We have an input parameter space and a point in that. We run that through the model, here G, and we get some kind of output which corresponds to the real world. This is Y in our output space. And we've got a statistical model which links those two things. So the game is to get a historical simulation as close to the real world as possible. You want your model to be adequate in some way and to represent the real world. So the technique that we're using for that is called history matching. And history matching, it's a form of calibration. After you've done a history matching process, you can go on and further and do a Bayesian sort of full probabilistic calibration. But history matching, we found, matches the way that modelers think about their models, the relationship between their models and the real world. And we talked about this yesterday, this idea that some modelers tend to think of their models as either adequate or not. They tend to rule out a lot of models. Oh, so we're going to ignore that one. And we can do a similar thing with a single model in a single structure when we think about which of the input parameters we would accept as being representative of the real world, or making our model basically run as if it was representative of the real world. So what we tend to do is run a large ensemble of simulations, choose a design from that input space, some kind of Latin hypercube or some space-failing design, and then basically compare that with observations, and then rule out parts of that space, of that model input space, where we don't think the model is adequate, essentially. So that's history matching. We tend to use emulators for that kind of thing, so statistical or machine learning models to represent our uncertainty, but also because we can't run the simulator, the full model, enough. It's computationally expensive. So we're using, we tend to use a Gaussian process emulator, so it's been great to see lots of Gaussian process use in this community. And all that's doing is basically interpolating between our model simulations and giving us some estimate of the uncertainty of the model output. So this is great. So we've got a large number of input parameters in Joules which are uncertain. We've got 32 in our particular case. We're looking at historical simulations, so 1850 to 2014. There's a lot of uncertainty in what happened in the carbon cycle and the land surface during that period. So we've got Joules, which is reanalysis driven, so it's driven by a combination of models and observations. And in particular, it's got a long spin up, a really long spin up. If you want the land surface to come into equilibrium, then you have to run the model for a long time before you start the historical simulation, in order that nothing's being dynamic. You know, you want it basically stable at 1850. And that's important later on. So we're looking at global land surface carbon outputs. This is very much a sort of data-driven. Can we do a data-driven calibration? So it's a kind of top-down exploratory ensemble that we're running. We've got about 500 members in the first wave of history matching, and then we've got another budget of more members. So history matching is an iterative process. Basically, you run an ensemble, you spread your net wide and trying to get as much uncertainty captured as possible, so that you're interpolating with your emulator, and then you narrow in, you focus in on a smaller and smaller part of that input parameter space that you think is adequate. So here is our design. These are the input parameters we've got. They don't really matter what they are at the moment, but the output looks kind of like this. So this is quite busy. These are the time series of these kind of global carbon properties of the model. So you've got MPP and the amount of carbon in the soil, that kind of thing. So just the down on the right here is a zoom in of the top left corner of that. So we've got a really wide range of behavior within the model. You know, MPP can be up to 100. Ensemble, we get quite a lot of members which are actually zero. So this is basically saying that there is no functioning carbon cycle whatsoever in our model, and I think we can safely rule those out. And in fact, they don't help at all. In fact, they make our emulators worse. If you include the zero, it's so far from being adequate that it's actually making our emulators worse, and at the same time it's costing us quite a lot of compute time and we've got a significant number of these for the spin-up, right? So the spin-up is a long, expensive process. So we want to get rid of those. So what can we do about that? This is actually a fun classification problem. So it turns out that there's only really three model outcomes here. There's RAN, which is good. We've got an adequate simulation, at least first pass. Some of these models have crashed, and some of these have got low carbon. So some of them have got zero carbon, essentially. And that sounds like a classification problem to me. So we can use a classifier to help get rid of the really bad space and help our history matching process work better. Here. So this is a pairs plot. This is basically each one of those little tiny squares is a two-dimensional representation of the input space projected through all the other 30 inputs. So essentially this is like a 32-dimensional cube which has been squished down to 2 dimensions in each of those little plots there. And the neural networks, which are sort of your brains, are picking up a pattern here, right? So okay, so maybe we've got some idea that we could do some machine learning and predict some of this stuff. Is this one here, which is this is our entire sort of range of parameters from 0 up to 1 once you've normalized them for BWL and F0IO, and it doesn't really matter what they are. This is what happens if you run within that space. Okay, that's a 2-dimensional space. Essentially, you're getting quite a lot. The blue points here are low carbon. The RAN I've not plotted here; they're sort of behind. Basically, you're getting some interesting threshold behavior here. So if you're beyond some thresholds, you have essentially crashed the model or given it a low carbon state or zero carbon state. This looks like a really good opportunity to use some kind of classification tool. Here we're using a random forest classifier. And basically a random forest is like a decision tree classifier, which we can run on this, and it gives us these nice thresholds where we can divide up the input space recursively into smaller and smaller parts. We're trying to keep the smaller parts of input space as pure as possible, essentially, to one class, and make a prediction on what's going to happen if you run at a particular input parameter set. So our decision tree has already picked out F0 and BWL IO as being important. We're going to take our decision tree and we're going to make it into a random forest. That is, we're going to train a very large number of decision trees on subsets of our training data, and then we're going to aggregate the results at the end. So we're going to take that training data with replacement, and we're going to build a classifier at each point, and then we're going to aggregate those results. Does it work? It kind of works. It works pretty well. If this worked perfectly, you would expect to see zeros on all of the off-diagonal elements of the confusion matrix here. But you can see it's getting most things right. It tends to over-predict crashed when they should be ran, but that might be due to how those members are spread through our input space. On the test set, again, it's not perfect, but it does quite well. But the fun thing is, I should say, just technically, we've oversampled from rarer classes, or we don't predict crash at all. So we've got a class imbalance problem here, but there are standard ways of doing that. I haven't optimized this perfectly. This is the start of a sort of student project, so there's a lot more work to do on this. But the fun thing is that you get that pairs plot back out again, and this time you get a probability that the model crashes, or probability in this case that the model runs. So you get from the random forest, you can get some look at the input space and see if it makes sense. And it does. Again, we're going to zoom in because this is very busy. But again, we're looking at 2-dimensional samples from that large previous diagram, and we're looking at the probability of each of the 3 classes in this case. So if my low carbon is the fun one. How do you predict whether you're going to have a low carbon state in this model? Well, if you run it at a high F0 IO, then you will have a high probability of having a low carbon state. So there's clearly some threshold behavior going on there in the model. If you want to invert that and you want the probability that the model ran, then that's the right-hand side plot. Essentially, the more yellow, the higher the probability. And you can see that as you go down into the into the bottom corner of a low F0 and a high BWIL, you basically have a higher probability that the model will run. So this is great fun. It's kind of useful to feed back to the modelers. It also gives you an automatic sort of variable importance plot, and it also gives you back these kind of partial dependence. You can see where the thresholds are or how the model behavior changes as you go across that input space. And these are really useful to go back to the modelers with and say, look, here's where your model is doing something weird. Here is where your model is experiencing some problem or has a particularly high bias. That's the kind of thing that we're going to. So in conclusion, so we fit this random forest as a start to basically as a tool, not only to help our history matching process, but also to feed back information to those modelers. We're predicting the probability of some kind of simulation failure, and this is a very simple example, but I've seen this turn up in other modeling systems. My PhD was on modeling the probability of AMOC collapse, and very similar results there. I've seen it elsewhere. So we know this is a kind of common feature of models, and that we could probably save quite a lot of compute time. And we're feeding back that information to the model developers. So next steps, I've got a student that's coming on to improve this classifier and do a better job. And then we're going to integrate that into this history matching process. And I'm really excited to see Fiona's talk tomorrow, developing random forest regression emulators as well. So I think that random forest as an emulation device is going to turn up more and more. I guess I've got one final slide. So last sort of 15 years ago, like Tamsin, we've been sort of trying to develop uncertainty quantification methods for these big deterministic simulators. And at the moment, this is the kind of cycle of climate modeling. We've got this kind of developing model and comparisons through observations and identifying these deficiencies. And out of that, you get these calibrated projections and downscaling and all the risk analysis, all the fun stuff that you get that's really useful for policymakers or people making decisions on the ground. And there's always been a human in the loop on that. You know, the model development process is a very human process, and therefore there are a lot of biases in the models quite often, especially when you couple them up. But that's increasingly becoming driven by, machine learning, which is super exciting. Thanks very much, Peter, for a fascinating talk. Very exciting. I would say we have got structural error problems in the models that are really important. We've just got to the point where we've got a lot of these methods now for looking at structural error and how that might impact on future climate projections. And I'm just saying to people who are developing these methods in machine learning, please take into account, I'm sure you will, structural error as you go forward, because it's probably the most important one. I'm getting a flashy screen now, so thanks very much for listening, and you can follow me on various social media or have a look at the paper for the Jules Ensemble there. Thank you.
Thanks, Doug. And now we're moving from surface up to the atmosphere. I know we have Hannah Christensen from University of Oxford talking about stochastic parameterization. Right, Hannah?
Great. Perfect. Great. Thank you so much. It's a real pleasure to be here today. So today I'm going to be talking to you about machine learning for stochastic parameterization, and I'd like to highlight my co-authors of this paper, then Salah Cohen, Greta Miller, and Ragul Parthapan. And I know that Greta is in the room here, and I think Ragul is joining us online today. So an outline for the talk: we're going to start off by talking about what parameterization is, then stochastic parameterization, before finally bringing in the machine learning aspect. So firstly, what is parameterization? So the problem that I'm interested in here is building a computer model that we use to make a weather or a climate prediction. And so the first thing that we do when we build such a computer model is we start off by taking 6 equations which describe the atmosphere, the ocean, and we discretize them onto some grid. And that's what's shown schematically here in this image. And this grid might have a length scale of order a few kilometers in a weather forecasting model, but it might have a length scale of the order of like 50 to 100 kilometers in a climate model. So this means that there's a lot of stuff going on at scales smaller than this grid box, this degree of pixelization, which we have to represent in some way. And this is where parameterization schemes come in. So here I've got two different call-out boxes showing us the kind of parameterization schemes we have in the atmosphere and in the ocean. Let's look in the atmosphere. In the atmosphere, we have things like convective thunderstorms, clouds, radiation, as well as turbulent processes. And you can see that these are acting in a column in both the atmosphere and the ocean. And so this problem of parameterization has drawn a lot of interest from the machine learning community over the last few years. These parameterizations are approximations of the true processes that are going on. So this means that the area is ripe for coming up with a machine-learned model which can improve upon the kind of simplifications that we've built in by hand to these models. And secondly, the parameterization schemes are really expensive. I think not many people realize this, but in a kind of typical weather forecasting model, the parameterization schemes account for about 50% of the compute time. So if we can come up with a machine learning approach, we can most certainly emulate the existing schemes to make them a lot cheaper. We can spend this compute time elsewhere, but we could also emulate and possibly improve on them at the same time. This means that we've got a lot of interest in this area for making machine learning models. And so, an approach that you might say come up with learning a machine-learned parameterization which improves on the state of the art. You could start off by taking some free-running, high-resolution simulation as your benchmark. This is the data set that's got the variability in it that you'd like to represent in your forecast model better. We can then coarse grain this data set down to the resolution that we're interested in for our forecast model. So say that's maybe 50 kilometers for a climate model. And then our task that we have is to come up with a way of stepping this field forward in time using a machine learning algorithm. We can then compare what we've predicted to the true coarse grain data at a later time. We can build this into our loss function and use it to update our machine learning model. And this approach which I've described here has been done to great success, but it's typically done in what I would say is a deterministic manner. So this means that the inputs that we give to our machine learning model is the temperature as a function of height, the wind as a function of height, the humidity and so on. And we then use this state to give us a deterministic, a single prediction of what the change in the state should be because of these unresolved physical processes. So we have this one-to-one mapping between the pixel level data that we have and the impact of these unresolved states. But the problem is that this is quite a big approximation that we are making ourselves in the setup of this problem, which we know is not accurate. And so I'm going to use this slide to try and explain how we know that's not the case. So what I'm showing here is actually results from using a more traditional parameterization scheme to do that stepping forward in time, but comparing the output of a kind of conventional low-resolution parameterization to what we know happens in a high-resolution simulation. So what I've done is I've made many of these kind of paired predictions, what a low-resolution parameterization says would happen compared to this high-res data set. And I've sorted my data according to what the parameterization scheme had predicted. And that's what is shown in the different subpanels here and highlighted by the grey vertical line in each figure. So for each then set of data, so for example, if we take panel D, for this set where our parameterization schemes say there's basically no warming, you can look at what really happened in this higher resolution data set. And the black curve there is the probability distribution of the true heating tendencies that you saw in that much higher detail simulation. And you can see that they're centered on 0 for this panel D, but it's by no means the same delta function. So there's an uncertainty associated. As we go to higher and higher warming tendencies as predicted by our deterministic parameterization, this is going along the lower panel here, we see a shift then in our PDF to higher and higher values, but we're also seeing a large spread here. So there's a lot of uncertainty that is associated with this parameterization process, which we're not capturing in this deterministic scheme. And this is because of a kind of a physical idea that we have. So the variables that we have on this grid scale, the low resolution temperature and humidity and so on, are not sufficient to constrain what is going on at the smaller scales. And so we should move away from this deterministic paradigm where we're always trying to predict like the most likely cloud, for example, in a column. And we should move to a paradigm where we try and predict one likely evolution of these small scales. And I should say that this is exactly the change in paradigm which was motivated by the talk yesterday about GenCast. So scheme. We're moving away from predicting the most likely outcome to predicting one possible outcome of the model. So yes, so we call these schemes stochastic parameterizations. We build random numbers into them from the outset, which enables us to sample from this probability distribution, and then effectively have this kind of Monte Carlo simulation where we explore this uncertainty introduced by the small scale variability. So this then brings me on to the challenges and considerations that we have when we want to build a machine-learned stochastic parameterization. So the first set of issues to consider is all our kind of physical constraints. And these are exactly the same kind of constraints and considerations that we have when we're building a more traditional deterministic machine-learned model. And there's been a huge amount of literature looking at these problems of conservation, extrapolation, and so on. So we're not going to talk about those here. Instead, I'm going to focus on two of the challenges introduced by this need to do uncertainty quantification within the parameterization process. So firstly, the most obvious one, we're going to have to start off by learning the probability distribution for our small-scale process. So as a case study of where we've used machine learning to do this, I want to talk about some work which was done by Greta Miller. This is really an advert for her poster, actually, so you should go along and see her later this afternoon. So the problem that we've identified is that models have a real issue in parameterizing where and when convective thunderstorms should occur. And so the reason this is a problem is because when you step through a kind of conventional weather forecasting model, we don't always call the bit of the code that represents convective thunderstorms. So before that bit of the code, there's an if statement. And this if statement is trying to assess whether there is convective instability and whether we should trigger the code. And the conventional predictors that we use are deterministic, and we know that they're a massive source of error in our forecasts. And we also know that part of this is because there isn't this one-to-one correspondence between the resolve scale and the state and the presence of a storm. So the solution that we've tested is to train a random forest to predict the likelihood of convection given the resolve scale state. We've trained this and as a proof of concept so far, we've been focusing on the ARM Southern Great Plains data set, which is a very high quality observational data set, but Greta's currently extending this to a more global data set. And what we find is that the random forest performs remarkably well. So here I'm showing the daily cycle in the amount of convection that we have. So black is showing you the observed frequency of convection throughout the day. So you see in this site it peaks around 6 o'clock in the morning. And then the different coloured lines is the predicted frequency or probability of convection coming from these different triggers we have. So conventional triggers include this one called CAPE and dilute CAPE. This is about how much energy there is in the atmosphere. And you can see how abysmal they are. They actually have the timing of convection wrong. But our random forest model here, this green line, actually has the probability well calibrated and the timing well calibrated. So we find this really encouraging. And then I should say what you can talk to Greta about in particular is how she's then gone in and used different XAI techniques to understand more what this tells us about the predictors of convection. What can we learn about the predictability, the probability of convection for different large-scale states? But what's also really important from our stochastic parameterization point of view is that the random forest is giving us predictions which are reliable. So where the forecast probability of convection, which is here on the x-axis, is a good predictor for the the cases in our testing data set and sorted them by what the random forest predicted would happen. You put the different data into bins according to this probability and then compute the frequency in each bin. So here, for example, we've got all the days that the random forest said that there was a 40% chance of convection, and you can see that it does indeed convect on 40% of those days. So it's reliable. The other thing is that it has good resolution. So that means that these probabilities really span the probability space. We're not always getting predictions which are around 0.1, which is the kind of climatological probability. So the random forest is able to kind of stick its neck out and say, yes, today is really likely to have a storm, and today it's not. And we think some of this good behavior comes from the kind of the random forest architecture itself somehow, that it's averaging over many different decision trees, thereby accounting for uncertainty in the classification process. The second topic to consider here is this topic of spatiotemporal correlations. And I really want to highlight that learning the probability distribution is only one half of the problem of stochastic parameterization. We then have to know how to draw from the distribution. And what we know is that it's really important to make these draws correlated in space and in time. So an approach that we've used to start addressing this problem is to use recurrent neural networks to at least get us the temporal correlations. And RNNs, recurrent neural networks, are really optimal for this problem because they're designed to reproduce a time series. And they also, one way that they can do this is that they learn this hidden state, which they track in time, which allows it to capture long timescale correlations. Ragul Parthapan, who's at the University of Cambridge, has tested this approach on a toy atmospheric model. The things you should know about this is that X is the large-scale resolved state, so this is things like temperature and humidity in this model. And then the tendency, the change in that state over a time step, we've split up into a predictable component, which you can determine from this resolved state, and an unpredictable component. And he's attacked the problem then in two stages, so using a simple neural network to give us the predictable component, and then the recurrent neural network to help us predict this, the evolution of this unresolved state, this unpredictable part of the unresolved state in time, which he generates stochastically using the RNN. And what we find is that this is a really skillful approach. It's able to outperform kind of benchmarks that we have on both weather and climate timescales. So on the left-hand plot, we have a comparison of the spread error. This is a little bit like what we saw yesterday in Ilan's talk on GenCast. So what we want here is a match between the error, which is the solid line, and the spread, which is the dashed line. And for the RNN, the blue, you see that we have the best match here for the weather timescales. And on the climate here, I'm showing you results looking at kind of the structure of the distribution of this model, where we actually have this unusual regime behavior. And again, we see an improvement here for the RNN compared to these other two benchmarks when we look at the truth. So the final comment to say is, with any machine learning problem, we need to have a good source of data. And the thing I really want to emphasize is that any data set that you can use for deterministic machine learned parameterizations can also be used for this problem. It's just a case of reframing the problem in your mind. So instead of using a loss function that is a mean square error, you need to come up with a different approach. You're predicting a probability distribution and then changing on log likelihood, for example. But we also have another data source which is being produced as we speak, which will be really useful for this problem. And this is a data set produced by an intercomparison called the Model Uncertainty MIP. And here what we're doing is we're creating a data set of short timescale errors associated with a whole bunch of different low-resolution forecasting models. And this is actually a way that we can then try and build a stochastic kind of error correction term for our more conventional parameterizations, a little bit like the framework that Ragul used in that last project. And so that then brings me to my conclusion slide. So we find that stochastic parameterizations are a really useful way for representing model uncertainty in weather and climate models. And we think there's a great potential to learn improved parameterizations from model data, but also learning about the predictability of the Earth system along the way. So thank you very much for listening. This talk was based on a full paper that we submitted to this conference and in which we hope will be published in Environmental Data Science afterwards, but it's already available on the archive. So if you want more details and more examples and so on, then please check out this paper. So thank you.
Thanks, Hannah. I would like to invite all the two to the stage, and we have 15 minutes for Q&A. We have already few questions on the Slido at the moment, and so we're going to also have the handheld mic in the room in case there's questions in person. Right. Any questions from the room for now? Oh, there's one in the back.
Hi, this is for the chap on the left. Just remind me of your name.
Oscar.
Oscar. You don't look like your picture from here. Maybe it's just my glasses.
I had blonde hair.
Nice. Yeah, maybe a stupid question, if that's all right. The first one is, with message passing, does that have a relationship with cellular automata?
Ooh.
And then the second one is maybe a suggestion and a bit left field one. I wondered, with the work that you're doing, if there's something around Turing's work with the chemical basis of morphogenesis to think about in kind of you working with these patterns passing messages to one another, and actually what happens when they don't agree and you allow the edges to kind of do different things. So I'm quite interested in what happens when you don't do the message passing.
So when you say cellular automata, do you mean like Conway's Game of Life style thing? I mean, I know if there's a relationship. I guess it's a similar setup, so maybe you can see some of the same behaviors in the way the state evolves. And then what your second question was, could you?
Yeah, so I think it's 1956 paper, Alan Turing's chemical basis of morphogenesis. I'm a biologist by background. So looking at pattern formations in plants and animals on the skin, like a leopard's, that kind of thing. I think maybe there's something interesting about these interactions between the different cells and the messaging that's passing between them, and there's a biological chemical basis for that. So I just wondered if that's something to look to in terms of what you're doing and how that might work for the work that you're doing.
Yeah, that could definitely be interesting. So I think people have looked into the weather variables are sending messages to each other, and one question is how do you schedule which message to send when to kind of speed up the convergence. And so it's possible, I know there's lots of work on this already that I don't really know much about, but it's possible that there could be some stuff to learn from what you're talking about, and I will come and find you later to learn more.
Thanks. I like the diversity of the audience in the conference today. So we have question online for Doug. Results advancing the theory behind these, for example, for the carbon cycles.
Wow, okay. So I guess we've got some tools from the Stone Age, but tools from the Stone Age can still be useful. And I see, well, it's such an exciting time. It was great to have Peter's talk earlier. We've got a lot of these methods. I think there's a lot of uncertainty in how machine learning is going to work in the future, whether we can actually learn the rules of the underlying processes. I think that's super exciting. If we can, then this is a completely new thing that we're going to be doing. In the meantime, we're applying a lot of new, exciting techniques to problems that we already have. We're trying to reduce the amount of computational expense. We don't want to. We've got large, extremely carbon-intensive computing. We want to minimize that as much as possible and increase our value for the people who are funding us. So we've got a huge amount using these kind of machine learning techniques. So definitely uncertainty quantification. I'm particularly interested in using some of these techniques to create better models, basically better informed climate modelers who have got new techniques for looking at the difference between their model and the real world and minimizing that as fast as possible, basically creating better models as quickly as possible. So while I still think that we should be absolutely exploring pure machine learning techniques for climate prediction, and they will come, there's a lot we could do with the infrastructure we have right now.
Great, thanks. Yeah, there's a question in the room. This gentleman first.
Hello.
Can you introduce yourself?
Yes, I'm Daniel D'Souza from UCL, PhD student. I have a question for Doug and Hannah. I guess it's kind of related in the sense of like Stone Age methods. I thought it was interesting that both of you use random forests, one for classification, other one for like distribution matching in some sense. I was wondering, because it wasn't like explicitly said, like what was the appeal of those methods for you? Was it because they're well established? Was it because of, I guess there was a quick mention of like explainable AI and how you can easily like investigate those tree classifiers. So, yes.
Yeah, thank you. So we tested a couple of different methods, and the random forest seemed to perform the best. So that's one reason why we then pushed it forward. And when I say the best, I mean in terms of the calibration of the probabilities that were coming out of it. But then, as you alluded to, the other appeal is then the explainability aspects. So it's very easy to then see which of the input variables are being used to make the decisions that it's making.
Yeah, for me, very much a pragmatic choice. It was pre-established, works well with the kind of number of ensemble members that we have. Basically, the data set up, we got a relatively small data set compared to some of the neural network type training situations. You get probabilistic output and it works. So we tried other classification methods as well, but the random forest work better than others.
Thank you.
Thank you.
We're going to take one online question and then go to Peter. The question is for Oscar. Is your method extendable to irregular grids? So where the grid cells are the regular in size or even change over time?
So I think probably yes, but I'm not sure.
More work. That's called job security, right? Right. Peter?
Thank you. Yes, I have a question for Hannah. You're basically learning like a stochastic representation of the subgrid scale out of the data, and you mentioned as well that you represent the if statements as well to some extent, like triggering of convection, for example, and stuff like this. And these can be kind of quite a nightmare in data simulation. Like for Fadivar, for example, if you would like to kind of also assimilate lighting data, but it's really tricky with these kind of if statements that whether you actually had got a convection or not. Is there anything that can be learned from your representation for data simulation in that context? I mean, have you ever thought about that? It's maybe an unfair question. But
yeah, it's not something I've thought about at all, actually. So I suppose, I don't know, I mean, a probabilistic trigger is a much softer if statement somehow than a binary trigger. These kind of conventional triggers that are used for convection are, does this computed convective potential energy exceed some threshold, and then it is yes or no. Whereas here we would then have some, we have some probability which you sample from the distribution in some way. And so I don't know if there's any kind of niceties actually of the fact that then you've got this continuous variable involved which can help. But I really don't know actually. You should talk more.
No worries, thanks a lot.
Thanks. I'm going to give the chance to the panelists to ask if you have any questions for each other. Because it's always not fair that when you are presenting, you don't get a chance to ask other people questions.
It's a good problem. We are focused on our own talks. That's the problem. No.
That's fair.
I'm kidding. I'm good.
One more question for online for Oscar is that have you considered adding edges between further away neighbors? So lower resolution grids connected to the higher resolution grids.
Yeah, so I guess there's two things going on. One, the pictures I showed in the slide were actually simplified. So actually, when you discretize the SPD and convert it into the graph, there are like connections, so not just the neighbors, but the neighbors but one. So I guess that's one thing. But then the other thing is, I guess maybe you could describe it as like a multi-grid approach. So we have connections to much further away in the grid. And we do actually do this. So in the actual algorithm, we use a multi-grid approach where we operate on a lower, coarser grid and then slowly refine to a high-resolution grid because that speeds up convergence. And from our experiments, it also seems to allow the thing to like take into account features that are further away. But I think we need to investigate that more.
Great, thanks. Any other questions in the room? Yes.
It's more a curiosity for Hannah. When you were showing the plot for the agreement for the real probability to the different metrics, and you were showing that CAPE is like higher than anyone, how you compute that? I mean, is given some threshold that we were saying, and if so, can it be just that the threshold is too low, the one that we usually use?
Yeah, thank you. So we did actually optimize the CAPE threshold for the data set. So we in what we felt was a fair way. So based on the training data set, we came up with an optimal CAPE threshold, which we then used for the test data set. So you might then say like, oh, but why is the probabilities far too high? It's clearly not optimized. But I mean, it depends. I mean, CAPE is just a really bad trigger. So if you set the threshold too low, then you miss a lot of your events. So you kind of, the way that we optimize is through a kind of like a decision grid. You have predicted events, and how many events do you hit and how many do you miss, and then predicted non-events, how many are misses and hits and so on. So we kind of optimize in this this kind of decision metric approach, and then
Do they have different weights, different importances, or are they all equally important?
That's a really good question. You should ask Greta, I think.
Great. I'm going to ask a question for Hannah. Since I work for a data center, and you're talking about model uncertainty MIB intercomparison, so I got super excited and then want to know how you're going to try to distribute the data like generated for the uncertainty MIB.
Yeah, thank you. So our plan is to host it on the British Climate Data Centre, so the kind of CEDA BADC centre with Jasmine.
All the participating group will generate data,
exactly.
And then it's all put into
Yeah. So we've got 4 modelling groups who are doing experiments. The NOAA NCAR Developmental Testbed Centre are actually running 2 different versions of their model, but we'll port that over to the UK to host here. And then Météo France are running their model, the UK Met Office are running theirs, and we're running the ECMWF IFS. So we should have 4, kind of 5 models.
Right. Any other questions in the room? What? Yeah, Tom.
Yeah, hi, Tom, Google DeepMind. And Oscar, I have a question about the message passing algorithm. So how do you train the edge functions, for example? You said you train like the prior or near 5 or something. And can I also just append a question for Doug, which you can think about while Oscar answers, but it hopefully is quite simple. When Jules fails, like what are the errors that are happening? Like, is it how far through the simulation is it typically when it fails? Is it some physical property is lost, or yeah? Thanks.
Yeah, so I think it was basically my explanation not being clear enough. So the edges basically come from the SPD. So we're assuming you have an SPD from somewhere, and that's where you can basically just rewrite it to eventually get it into this factorized form, and then that gives us the edges. And then the prior, what I was saying there was that in our experiments, we wanted to do like a sort of fake data assimilation experiment. So what we do is we, as our existing state of the simulator, we use era 5, and then we assimilate some temperature observations, which are also from era 5, but we've like put onto satellite tracks, and that's the assimilation problem we're working with. Does that make sense?
Right. Thanks.
Oh, I just had for Tom on Joule's failure. So when it goes to low carbon, a low carbon state, it's often in similar ways. So essentially, there were those two parameters. You go through some threshold, and it just sort of completely destroys the carbon cycle. So that's easy. The problem with the crashes is that they all happen in different ways, and you'd have to ask the modelers. I'm not a land surface modeler, so I work with the land surface modelers. And that's reflected in the fact that they are more evenly spread throughout the parameter space, and they're much more difficult. The problem with the low carbon ones is they run all the way to the end, and they're expensive, so we've got to put something in to stop that. The crashed ones don't always run through to the end, but sometimes they do, so they're really annoying. So a fun thing to do would be to rebuild this, but look at the early part of the spin up in order to try and predict the end of the spin up, and that would probably save us a lot of computation as well. Thanks.
Thanks. I think that's all of our time, and please thanks all the speakers again, and we will have 30 minutes coffee and snacks break before we come back for our panel on reproducibility.